Hello everyone, this video is for section 3.1, which introduces the derivative. The derivative happens to be an extremely important topic in calculus. It's basically what calculus is based off of. So the derivative, extremely important, and we're going to focus this week on where the derivative comes from and what it represents. Next week we will be learning some shortcuts that allow us to find derivatives quickly. And quick is not the focus of this week. This week we are planning to do the derivative essentially the long way, and hopefully we get a better understanding of where it comes from. So let's first start off by defining what the derivative is, and then we'll also discuss some notation for the derivative. So a definition for the derivative, a very loose definition in terms of what it represents, is that it is actually the instantaneous rate of change, which we should be familiar with from week 1. So a derivative is the instantaneous rate of change at a specific point. Okay, so we're talking about the slope of the tangent line at a specific point. Notation-wise, we have many notations for the derivative, but one of the most common ones is f prime of x. And so the prime symbol is that little, almost like an apostrophe, but straighter there, the f prime of x. So that is one that we use typically, x meaning the point at which we are finding the instantaneous rate of change. And when we say point, typically points have two coordinates, an x-coordinate and a y-coordinate, but we will often just refer to the x-coordinate in our discussion. So we're going to say that the point is where x is some given value. We also have this other common notation, dy over dx, which we can also think of as the change in y over the change in x, and you may be familiar with that triangle symbol to represent change that we've possibly seen in algebra. But that's what we're looking at here. We're looking at how y changes in comparison to how x changes, and commonly that is slope. And so the slope part comes from the slope of the tangent line. And again, that goes back to the fact that we're talking about the instantaneous rate of change, which is the slope of the tangent line, as opposed to the average rate of change, which is the slope of the secant. So there are actually several more notations for derivative, but those are the two most common ones, and those are the ones that we will use most often. Alright, so just to illustrate this concept with a diagram, I'm going to draw a function, and I'm going to call it f. Any old function will do. But if I pick an x value, and I go to the point on the function on the graph that corresponds to that x value, and I draw the tangent line at that point, that tangent line is going to have a slope which represents the derivative of the function at that point, f prime of x. Okay, our next discussion is going to be regarding when you can find a derivative and when you cannot find a derivative. So the ability to find a derivative is called differentiability. So differentiable is something that we need to define. Differentiable looks like that. So again, the differentiation part is the process of finding a derivative. So differentiable means that you are able to find the derivative. Which is not always the case. There are times where we are not able to find the derivative. And we're going to discuss a couple of those reasons as to why we may not be able to find the derivative. There we go. I just refocused there, so hopefully the written word here is a little bit more clear to read. Anyway, going back to our discussion here. So sometimes you're able to find the derivative and sometimes you can't. So let's discuss what the conditions are where you can and can't find the derivative. So we're going to start off by making a statement here that says, if our function f of x is in fact differentiable, then that same function f of x is also continuous. So if we are able to find the derivative of a function at a certain point, then we're saying that that function is continuous at that point. You have to be really careful not to switch that around to say that if it's continuous, then it's differentiable, because that's not always true. There are cases where that will be proven wrong. But we can always say that if it's differentiable, then it must be continuous automatically. Okay. Another way we can phrase this same thing is to say that if something is not continuous, then that automatically implies that it's not differentiable. Okay? So we're getting into some very minor semantics here, but we are not able to say that if something is continuous, then it's automatically differentiable. That's not always true. But what we can say with absolute certainty is that if it's not continuous, then it's absolutely not differentiable. So let's talk about some of the conditions that cause a function not to be differentiable. So when is a function not differentiable? All right, when is it not differentiable? And I'm going to discuss 3 different scenarios where a function would not be differentiable. The first scenario is that it would not be differentiable at a point of discontinuity. Because remember, if the function is not continuous, then it's not differentiable. So if we have a point of discontinuity, that obviously means that we're not continuous, and we're not going to be able to find the derivative of the function at that point. We can probably find the derivative at other points along the function, just not at that point of discontinuity. The second situation that we might run into where we would not be able to find the derivative at a point is if we have what's called a cusp point. And this isn't something that's come up so far in our calculus work. So let me illustrate to you what it means to be a cusp point. Let me quickly draw a graph here. I apologize for covering up my work with a ruler, but I like to have my lines straight as possible. Alright, so a cusp point. Here is an example of a cusp point. You are probably familiar with the graph of an absolute value function. Well, absolute value functions have, they're not smooth curves. They are 2 linear pieces that come together at a point. And by point, I don't mean just any xy value, but I mean a corner. All right, so something like this is called a cusp point. And we could not find the derivative of this function at that point. Okay, so we're not differentiable at a cusp point. We're still continuous, there's no problem there, but we're not differentiable at any cusp point. Alright, and then our last scenario is if we have a vertical tangent line. Alright, so if we had a function where we had a point and the tangent line was vertical at that point, that would mean that the slope was undefined. And when we have an undefined slope, we also have an undefined derivative. So we would not be able to find the derivative at any point that had a vertical tangent line. Alright, so those are the basics of basically what a derivative represents. Remember, it's the instantaneous rate of change or the slope of a tangent line. We also have talked about a couple of different notations that we could use, and when we are able to find a derivative and when we're not. So these are all things to remember. What we're going to do next is move on to actually doing some calculations in terms of finding a derivative. Okay, remember, like I said at the very beginning of this, we're going to do it the long way right now. This is all about developing the formula of where it comes from based on what you already know, rather than just pulling it out of the sky. And then next week, we're going to go over some shortcuts where we can find these derivatives in seconds rather than, 3 or 4 minutes. So that's what we're headed towards. All right, so the discussion next is about finding the derivative. So the actual formula for finding the derivative of a function at a point. So up until now, what we've done is we've calculated a bunch of slopes of secant lines, or a bunch of average rates of change. And over the course of making a table for maybe 8 or 9 different slopes of secants, we were able to predict what the limit would be in order to find the slope of the tangent line, or the instantaneous rate of change. And so this formula will eliminate the need to calculate several secant slopes in order to find the limit of a tangent, or in order to find the limit to create the slope of the tangent. Alright, so once again I'm going to give you a diagram here with an illustration of what we're going to be talking about. And so let's say I draw any old function. I'm going to create a function that looks something like that. And let's say we have some value x, and here's the corresponding point on that graph. Okay, so the coordinates of that point there are x, comma, f of x. Well, what we're going to do is we're going to take x and we're going to add some h value. Okay, we're not going to specify how many units we are going to add or what h is, but we can add anything to it. Okay, so we have an x value and we're going to add h to it, and what that means is that our new value that we've reached here on the x-axis is now x plus h. Again, we didn't know what the value of h was, but we took an x value, we added h to it, and we got to x plus h. So in terms of a corresponding point, the coordinates here would be x plus h, comma, f of x plus h. Alright, so the goal here is to find f prime of x. So what we want to do is we want to figure out what the slope of the tangent line at x would be. And so we're going to imagine that this h value here heads towards 0. So in other words, as we remember calculating several secant lines, let's say we were to